So we've seen some definitions by cases, a very simple function for computing the absolute value of a number. Without going into too much more Haskell, we can do some slightly more interesting things just with what we've seen so far, namely definitions by cases and simple computations over numbers. And the example we're going to use here is the power function, the exponentiation operator, which if we're to use it in the interpreter, we write in the form, for example, 2 to the power 3. So we're going to write this as a function called power with 2 arguments. And in this case, this would be 2 to the power 3 would be expressed by using power 2, 3. So this is going to be used to illustrate a definition using recursion. Now recursion is something which you will have, or at least should have, seen in other contexts in courses on, for example, general programming, data structures and so on. So hopefully the concept of recursion is not completely new, but if it is, I think this example should illustrate it fairly well. So we're going to define the power function, and we're going to define this not for general exponentiation, but just for exponentiation of some integer to a natural number power. So this would be a positive integer. So we're not going to define it for all values. We're just going to keep this fairly simple. So let's start off by defining a couple of cases. We're going to n to the power k, and we'll take the simplest case that we know, which is when k is equal to 0. And what's the answer when we take something to the power 0? Well, we take the identity operation for the exponentiation operator. It's just 1 to the power 0 is 1, for example. The other case that we're going to handle is the case when k is greater than 0. nk, I'm going to write this out. I'm not going to do any simplification just yet, so that's why I'm writing this out in longhand, as it were. So when k is greater than or equal to 0, then we're going to compute it using recursion. So what does that mean? Well, it's easily illustrated by this little example that I've given. If we're going to compute 2 to the power 3, what we're computing is 2 multiplied by 2 multiplied by 2. We're multiplying 2 by itself 3 times. And so the idea will be that we're going to compute this power in terms of a smaller power. We're going to compute it in terms of using power n k minus 1. So let's suppose we know how to compute n to the power k minus 1. For example, we know how to compute 2 to the power 2. We know how to compute this thing. If we've already computed this thing, how would we then build the answer that we want, which is power nk when k is greater than or equal to 0? So how do we compute this thing if we already know this thing? So how do we compute this thing if we already know this thing? Well, we multiply it by the 2. So to compute the power that we want from this thing, we simply have to multiply it by 1 more copy of n. Okay, so this is a very simple strategy for computing the power function. It works by recursion. We've defined power using itself. The reason it works in this case is because each time we use the power function, we use it with a smaller exponent. And eventually that exponent will reach this case, which we call the base case of the recursion, and give us the answer 1. So that means we can calculate sort of by hand that when we are computing 2, for example, to the power 3, what the Haskell interpreter will do is look at the definitions that we have for the power function and determine that this guard is false. So we have to move on to the second equation, and for the second equation, the guard is true. K, the value 3, is bigger than or equal to 0. And so we can now replace this thing, power 2, 3, by this thing, which will be the n, which is 2, multiplied by power 2 and 3 minus 1, which is, I'll just simplify on the spot, which is 2. And what happens next is that in order to multiply 2 by something, we need to work out what this something is. So we apply the rules again. Again, we apply this equation to simplify this further to 2 multiplied by 2 multiplied by power 2 and 1. And when we compute power 2, 1, that will simplify further to all of these things. And power 2, 1 will simplify to 2 times power of 2 and 0. And how do we compute power 2, 0? Well, that's a case when the k is equal to 0. So we use this equation. So this thing here will be the value 1. And now once this is computed to the value 1, these multiplications can all be finished, giving us 2 times 2 times 2 times 1, which gives us the value 8. So let's just reload that file and compute power 2 and 3. Oh, I'm not in scope. What's happened? I didn't save the file. I've saved the file. Let me reload that file. And we see that we do get indeed the expected answer. Now I'm not finished yet because I want to both simplify but also make this definition a little bit more complete. In particular, what happens if we do power on a negative number? We need brackets here for negative numbers because the minus sign is a little tricky beast because it has multiple meanings. It can be part of a literal, -2. It can be the negation operation that we used in the abs function, for example, -x. And it can also be a binary operator, which is the subtraction operator. So this little beast is a tricky one to parse. That's why we need brackets around our negative literals. But what happens when we try and compute this thing? Well, let's see what happens. We get an exception. And I want to think of you, basically this is a crash. We get an exception because there's no equation that matches. And the fact that there's no equation is expressed by the phrase here, non-exhaustive patterns in function power. And that is to say, the patterns that we have, the cases that we have in our definition by cases, don't cover all possible outcomes. They're not exhaustive. So when k is neither equal to 0 nor bigger than or equal to 0, I suppose we could have just as well written bigger than 0. When neither of those things are true, there can still be a match. It can be still negative, and we have no equation for what to do when it's negative, and so we get an exception. And that's okay. That's fine. It's not great to have functions that can throw exceptions in this way because there's no way, we don't have any way of recovering from those. But it could be that, if the intended use, if we're careful with the intended use and make sure that we only use this power function with non-negative exponents, then we maybe could be okay. But it can be nice to have, instead of giving this standard error message, to actually give our own error message. And we can do that by actually writing a case for this. And again, I'm writing it all in full, but I'll simplify. And I will use the otherwise here. So in this case, we can't. There's no value that we can give. We want to actually give an exception because that's what we're intending to do. But we can do so with our own error message. And we do so with this function called error, which throws an exception, and you give it a string containing the error message. So I've said power with a negative exponent not supported. Oh, it's quite a long line. And you might think, oh, that's not very nice. Well, no, it's not very nice to read on this little small screen. But we can actually put in line breaks any way we like, as long as we indent this more than one space. So we can't do that, but we can do that. So I'll indent it a few spaces and put it on the next line. Okay, so we now have a version of the power function, which when we try it out on a negative exponent, we'll still get an exception, but we'll get it with our own error message. No big deal, really. Okay, I want us now simplify this just a little bit to illustrate a couple of things. And the first thing is that this first equation can be written in a slightly different way. Instead of using guards, testing whether k is equal to 0, we can actually use the value 0 on the left-hand side. And we can do it in the following way. We can say that power n and 0 to the n to the power 0, power n 0 is equal to 1. So we can use values. We can't use anything we like, but we can use values like 0, like true and false, in the left-hand side. And this is an example of something we'll see a lot more of in the next lectures. This is an example of something called pattern matching. So we're giving a definition using pattern matching. We're saying that if the argument matches this pattern, it's a 0. in this case, then the answer is 1. Otherwise, power n to the k if k is greater than 0 is this, and so on and so forth. Now you may also remember that when we have two equations with the same left-hand side, power nk and power nk, we can actually group them together into a single one. So I'll do that now to give me something which looks more like the absolute value function example that we looked at earlier, and I'm just adjusting the spaces so that maybe I'll push them in a bit so they all line up, and that'll make it a little bit more readable. Okay, so there's the example of the power function, and I calculated this in a series of steps, and I'll turn that into a list. I'll make this list run over several lines. We haven't talked about lists yet, but it's one of the standard data structures built into Haskell. And what I'm doing here is just writing each of these expressions as an element of a list. A list starts with a square bracket and ends with a square bracket, and I can actually break this over multiple lines. And one little stylistic way of doing that is to write each line beginning with the comma that separates to the next guy. So there's a series of, these are the computation steps that the power function will go through when it computes power 2 to the power 3. So there are 1, 2, 3 recursive steps before we get to the final one, which would be when this one replaced by 0. I can write that one in just to be complete. We'd have 2 times 2 times 2 times the final recursion. The base case of the recursion is the value 1. And so that's what our series of computation steps would look like in that example. And actually, if you note, if I reload, get rid of capitals there, reload that file, if I look at that example, what do you think that it will give you? Well, it'll just give me 2 to the power 3 repeated 1, 2, 3, 4, 5 times. And there they are. Because, of course, each of these is equivalent to the previous step. These are just representing, we're just sort of picturing what the computation steps inside GHC might look like. Now, of course, we don't need to define the power function at all because there is an existing exponentiation operator, as we saw. But we can use then this as a specification for what this power function is supposed to do. So let's write a little quick check property then, just to tie the discussion of recursion together with the discussion of testing and quick check. Let's write a property of power for some n and some k, and that is that we are expecting that n to the power k using the built-in operator should be equal to power n k. That's a first attempt at a property, and let's see what that does. So let's compile that, and we'll just compile it. Let's just quick check that. Prop power, and see what quick check says. Quick check is going to test this by throwing random values at it, and what quick check observes is that very quickly, after just 3 tests, it found 2 values for which the test fails, that they're not equal. And they're not equal because power, of course, is undefined when the exponent is negative. Now, quick check didn't know to generate only non-negative exponents. So we need to fix this. We need to do the test, but we're not expecting this to work for all values of k, only the non-negative ones. So how can we do that? Well, we can use our good old function abs, and we could do that by putting abs in here. So we could do power abs, absolute value of k here, and we could also do it over here. We can take the absolute value of k here. So we're making sure that even though this k might be negative, we're only going to use the positive part of it. Now, what you notice there, I'm using the same computation in 2 places, and that's actually a bit wasteful. We shouldn't be computing this twice. We should only be doing it once. So a standard way to do this would be to make a local definition. We saw an example of that in the exchange rate, in the approximate equals function. That was what it was. So I'm going to use a k prime, and where I'm going to define k prime locally using a where, and that's just going to be the absolute value of k. So that's, I can move it over here, probably a bit more readable. So that's more like the property that we would like. Let's reload that and try it out. And indeed, it seems to be doing the job.